Happy Friday, everybody. Today we're going to talk a little bit about specific heats and some property approximations. I'm going to do a little bit of a review about the lecture, the very short lecture review, and then we will go in and solve some problems. Just so you know, right now the plan looks like I can get the exams graded and back to you on Wednesday of next week. It's a little bit later. I thought maybe I could do Monday, but it looks like Wednesday. I don't know how you are doing with all these online classes, but I am sucking air, trying to get through this. But we'll do sucking air. That doesn't really make sense, does it? Because we're all sucking air. I'm sucking is what I'll just leave it at that, and we'll see if we can't work on that. And I'm also going to send out a mid-semester T-Val, a feedback form for you to give me some things that I can improve upon, some things that you want me to know about. I think the T-Vals at the end of the semester are great, but they help the next semester. I want to help you guys. So be lookout for those two things as we progress through next week. Okay? So let's talk about the specific heats. Okay, so specific heats. We know there's two specific heats, C sub P and C sub V. And it's important to know how they were created and what they mean. Okay, just using them, you can get by with that. But if you understand what they mean, you can do more with them, understand them better. Okay, so C sub P means the specific heat at constant pressure. What is specific heat? I'm going to take 1 kilogram of material or 1 pound mass of material, and I want to see how much energy is required to raise that 1 kilogram or 1 pound 1 degree, either 1 degree Celsius or 1 degree Fahrenheit. And then I'm going to write it down. C sub P means I'm going to keep that system at constant pressure and find out how much energy needs to be added to that 1 kilogram, that 1 pound, to raise it 1 degree. C sub V means I take that system and I keep it at constant volume and see how much energy is required to raise it that 1 degree. Now this is going to be a different amount because when you're keeping something at a constant pressure, you're going to have expansion that happens. As you add heat, the tendency of that system is to want to increase in pressure. But if you relieve that pressure by increasing the volume, that's great. So in the C sub P, when I want to keep the system at a constant pressure and I'm adding energy, some of that energy is going to go into the potential energy change or the movement of that piston up. And then the rest of it's going to go into the change of the temperature. So therefore, the constant pressure specific heat is always going to be larger than the constant volume specific heat, because more energy is required for that system, because not all of it goes into temperature change. Some of it goes into that piston moving up. Okay, constant volume, going to be less than that. So C sub P is always greater than C sub V. Always. Okay, so let's just do here constant pressure. And this is constant volume. Now this causes problems to students. This is how we define it, and I think I repeated it at least 3 times. If I repeat something 3 times on a lecture, you know it's something that you probably should put a big star beside. Because students, even though these were created with constant pressure and created with constant volume, we do not have to use them exclusively in constant pressure or constant volume situations. That's how they were defined. That's how they were developed. Okay, that does not mean that's how they are used. And I worked for a long time, and it confused a lot of students. And then I came up with this analogy of duct tape, that we created duct tape for ducts, but then we don't use it for ducts. We use it for all sorts of other things. That's the same kind of idea that we have here. And you're not going to see it today, and you're not going to see it until the lecture on Monday, and then we're going to use it in class on Wednesday, why this is the case. And it has to do with the enthalpies and the internal energies. Okay, so there we defined what specific heats were, what it means, C sub P and C sub V. We talked a little bit about where you can find those in your tables. We'll look at that a little bit later. Then the next thing we did was we looked at the liquid approximation. we've talked about the liquid approximation before, but now we formally introduce it to the class, and that's just saying that any system that is a liquid, if I want to find the specific volume and I have given some temperature and pressure, I can assume that it's the same properties as the specific volume of the saturated liquid at whatever temperature I've given. The internal energy at some temperature and pressure is approximately equal to the internal energy of the saturated liquid at whatever temperature I've been given. And enthalpy at some temperature and pressure is approximately equal to the enthalpy of the saturated liquid at whatever temperature I've been given. Plus, there's some other term over here, some other very small term that's a correction factor. But it is so small, it's very small, that it often doesn't mean anything to us. And so I'm going to tell us right now, don't worry about that correction factor. Just worry about these things. If you see something that's a liquid and you want to do a liquid approximation, just assume that the properties are the same as the saturated liquid properties at whatever temperature you've been given. It's important that you do temperature. If you do the pressure you've been given, you're completely off. It only works for temperature. Okay. And then the last thing we talked about is something called the incompressible substance model. The incompressible substance model only works for incompressible substances. And so the incompressible substances that we're going to be talking about are liquids and solids. Yes, solids is easy. Solids are incompressible. But liquids, their bulk modulus is in the gigapascals. You need to put something on a gigapascal range to see a change in volume. And so they're basically incompressible. So we're modeling it. It's not correct. You can't say it's incompressible. It's not really incompressible. But for all intents and purposes, modeling it as incompressible is pretty good. It saves us a lot of time. It's pretty much true. But if we were to get down into the facts, you could not truly say it is incompressible. But for all intents and purposes, it is. And so when this happens, when we do that, we replace the change in internal energy with the specific heat times T2 minus T1. Remember here, I didn't state this, that for incompressible substance, C sub V is equal to C sub P, so we just call it C. It doesn't matter which one we use, because for incompressible substances, the C sub P and the C sub V are the same number. And it makes sense, because if we have an incompressible substance, that volume shouldn't be changing. So the amount of heat that you add to a system at constant pressure and constant volume should be the same. Okay? And also delta H is equal to C times T2 minus T1 plus some correction factor over here. But this again is small. And I underlined it on your equation sheet, and right now we just don't have to worry about that. So basically, for our incompressible substance, the change in internal energy is the same as our change in enthalpy. And that should make some sense when we look at the definition that H is equal to U plus PV. If we don't have any change in volume, we have no change in specific volume, this term really doesn't happen. So you have H is equal to U when you look at deltas. So if you can conceptually understand these ideas, then this in 8 minutes was what I lectured about. Okay, I was telling the students this morning at 8:30, and I don't know, I thought I'd do something, but some students are starting to write on their, they would write me a whole long email, and at the very end they would write TLDR, and I didn't know what TLDR meant. And then I finally read about it. I was on Reddit, and TLDR means too long didn't read, the too long didn't read version of it. Well, I'm giving you this lecture here is the TLDPA, the too long didn't pay attention version. Okay, this is all you need from that lecture. Okay, this is the brass tacks of it. Okay, I'm coining that term right now. So when it takes off, you were here when it started. Okay, and that's going to be a big selling point to your friends. So you're welcome. All right. How annoyed are you with my humor? Just super annoyed? Is it super annoying? Because it is annoying to my family. I asked my kids just a minute ago. I said, I was at home eating lunch with them, and I said, how annoying am I? And my daughter said, you're pretty annoying, Dad. So um, I appreciate her honesty. Any questions on this before we do a problem? So I'm going to do incompressible substance problems today, and I'm going to do those because it's a pretty easy concept. I'm going to do one problem that would be out of your homework, and one problem that the first problem I'm going to do is kind of not like your homework problem. The second one is like your homework problem. And I always ask this very similar homework problem every semester. And a couple years ago, I asked a question like that on the exam, and students just bombed it really, really poorly. And when they saw the answer, they were very disappointed in themselves. So I'm glad I had the opportunity here to do this kind of recitation and go into a little bit more detail and hopefully help you understand it a little bit better, because it's not a really difficult mathematical idea. So here's the problem that we're going to deal with, the first problem. I have a tank, and this tank has a heater in the bottom of it. And that heater is made of 0.25 kilograms of copper. And what we're going to do is we're going to pass electrical current into this copper, and this is going to be a heating element, basically. And we have to do something here. We're going to put 10 amps at 12 volts through it for 100 seconds. Now, those of you that are electrical engineers, this is your language we're speaking. Mechanicals look at that and say, "Oh man, volts and amps and time. I don't want to do that." But we'll figure this out together. Inside this tank, we have 0.15 kilograms of water. Okay, and what we're going to do is we're going to insulate this tank completely. And we're going to say that at state 1, the temperature of that tank, the water in the tank, but the water's in equilibrium with the copper, is 30 degrees Celsius. And what we want to know in state 2, we want to know what is the temperature at state 2 after that current has been put through that resistor and we have this heat that's happening here. What is our temperature at 2? Okay. So we look at this problem, and the first thing we see is, well, there's no mass coming in and out of whatever system we would choose. So this is a closed system. So I'm most likely, I am going to use the first law for a closed system, the change in kinetic energy plus the change in potential energy plus the change in internal energy is equal to Q minus W. And here I have a choice about what system to choose. And I've always told you, hey, choose the simplest system as possible. And what we've been doing so far, if I were you, I would say, okay, I'm going to choose the water as my system. So let's just see if I made the water as my system here. I know it's not moving. There's no velocity given. There's no height change given, so my kinetic energy and my potential energy effects are going to be negligible. This system up there has no work. There's no boundary work happening. There's no paddle wheel work. There's no electrical work happening. But I know there's going to be heat coming into that system because it's coming from the copper. Now, all I know about the copper is that there is some electricity coming into it. So I have this worry that I don't know how to find the heat transfer coming into it because I don't know anything about the copper. The other thing I'm worried about here is that I only know one thing about the water. I know it's at 30 degrees Celsius, and I know I have to have two things to set the state. And so this bothers me a little bit. That simple system is, we could solve that problem with the simple system, but then we would need to also make the copper a system and find out what the heat is leaving the copper and that would be the heat coming in to the water. We could do that, make two separate systems. Or I could suggest that we just make this whole thing the system. So that's what we're going to do. We're going to make the whole thing the system. There's not one way to do it. But this is the way that I would recommend. It's a little bit better way to solve. It involves a few less steps. Now still, in this green system, my kinetic energy and my potential energy still go to 0. In this system, now I can say that there is no heat leaving the system because I'm only concerned with what's crossing that boundary. I don't even care if there's copper and water and 73 other different things in there. I only care about what's crossing that green line, and there's nothing, so I can get rid of my heat transfer. But there is work coming into this system because it's electrical work. There's no boundary work, there's no paddle wheel work, there's no mechanical work, but there is electrical work coming into this system. So I'm going to have to calculate what that is. Okay? So how I would rewrite this equation now is I would have to say the change in internal energy of the water plus the change in internal energy of the copper. I have to split apart that delta U because the delta U is dependent upon the type of material. There's going to be a different change in internal energy for copper and water and everything in between. But there only happens to be two things here. On the other side of the equation, all we're cared about is what crosses the boundary, so we really don't have to break this up and just say what is the work of the copper or work of the water. It's only one thing, whatever's crossing that boundary. Okay, let's go ahead and first calculate what that work is, electrical work is. That's going to be, if we look on our equation sheet, it's going to be T1 to T2. It's going to be the voltage times the current times dt, or voltage times current is power. Power is the rate of work. If you take the rate of work times the time that you're working on, you will find out what the actual work is. Okay, this is on the equation sheet, so we don't have to really worry about that. But the voltage and the current are constant, and so you're going to be able to say this is equal to E I times our T2 minus T1. Okay, so this is going to be equal to our voltage was 12 volts. Our current is 10 amps, and we're taking it times 100 seconds. Okay. Now the units of work are going to be in kilojoules, and so we're going to have to do some conversions here, and the conversions that we have, 1 volt is equal 1 watt per amp, and we have 1 watt is equal to 1 joule per second. Okay, so let's see what that gives me. Volts cancel, amps cancel, seconds cancel, here this watts cancel, and I'm going to get units of joules. But usually in thermo I'm going to deal with kilojoules, so I'm going to go here and say, okay, 1,000 joules is 1 kilojoule. And when I go through, and now I have units that I want here, and I do this multiplication, actually this 10 times 100 is 1,000, and so it ends up that my answer here is just 12 kilojoules. But I have to remember that that is from the surroundings into the system. This equation doesn't give me the thermodynamic sign convention. The only thing that gives me the thermodynamic sign convention is that work is equal to the integral of PdV. That gives me the thermodynamic sign convention. This one does not. This is in, so when I put it into my equation, I'm going to use minus 12 kilojoules. Okay, so now up here on this top equation, I know what my work is. Now I have to look at my change in internal energy for my water and my change in internal energy for my copper. Now I think to myself, this equation should be the following. It should be mass times mass of the water times U2 minus U1 of the water plus mass of the copper times U2 minus U1 of the copper is going to equal to, here is a negative, it's going to equal to 12 kilojoules. Well, I do have some tables for water. I can look up water. I don't have tables for copper. no solid do I have tables for. So that immediately should get me to think, how do I find the properties for copper? Oh, copper's a solid, copper's incompressible. I can do the incompressible substance model. And my philosophy is, if I do the incompressible substance model for one thing, I should try to do it for the other thing. And water can be also considered incompressible, and so that's what we're going to do. We're going to say that's incompressible as well. Now, if it happened to be that water changed state from liquid to a liquid vapor in state 2, we couldn't do that because that liquid vapor is compressible. That vapor portion of it would be compressed. And so we would have to make the assumption right now that it would remain liquid, that the temperature would not go above 100 degrees Celsius. If we find that the temperature does go above 100 degrees Celsius, then we have to go back and say, hey, that was the wrong choice about our model. We always check to make sure our model works. But right now, I think that it will, so I'm going to go here and say, now I can say this is equal to the mass of the water times the specific heat of the water times T2 minus T1 of the water plus the mass of the copper times the specific heat of the copper times T2 minus T1 of the copper. Okay, and that's equal to 12 kilojoules. Okay. I was given in the problem statement what the mass of the water is. I was given in the problem statement what the initial temperature is, and we're going to come to an equilibrium final temperature, so T2 water and T2 copper are going to be the same temperature. We're coming to that equilibrium. I just need to go and find out what my specific heats are for copper and water. And so what I'll do is I'll pull out my handy-dandy appendices, and I'll go to table A19. And we're doing with SI, so A19, not A19E. And this is the table that provides us with all of the information for solids, properties for selected solids. And it gives us the specific heat, but it only gives us C sub P. And here it doesn't matter, C sub P or C sub V, because incompressible substances, we're saying the same numbers. Now, it gives it to us, its selected solids at 300 Kelvin. Okay, right now we're at 303 Kelvin, right? 30 degrees Celsius is 303 Kelvin. If we were to do this correctly, perfectly correctly, what we would want to do, we're assuming that the specific heat doesn't change. That's what we're doing here. We're assuming the specific heat is constant over the range of temperatures that we're at. That's the assumption we make. And specific heat does change with temperature. It does change with temperature. So, really, we should look at the initial temperature and the final temperature and we'll find out what the C sub P is at temperature 1 and what the C sub P is at temperature 2 and take the average of those and make that assumption. And use that value as our C sub P. But really, we don't have that information. All they gave to us is the selected solids at 300 Kelvin. So let's just go with it because we're assuming here, and it's a good assumption, that the specific heat doesn't change appreciably and we're going to be good to go. So we're going to use 0.385 for the kilojoules per kilogram Kelvin. So it's going to be 0.385 kilojoules per kilogram Kelvin. Now, water is a different story. Down here at water, they give us, because we deal with water quite a lot, they give us the specific heat at a lot of different temperatures, 275 Kelvin, 300 Kelvin, 325 Kelvin, 350, so on and so forth. And you see it does change. It's not a lot of change, but it is some change how the specific heat changes. So we start at about 303 Kelvin, and we're going to assume this is going to go higher. So what I could do is I could say, okay, I'm going to average these two specific heats and take the middle value and go with it. That would be an acceptable way to solve this problem. But what I'm going to do is say, since I just assumed 300 for copper, I'm going to assume 300 for water and put 4.179 into it. If you were doing on the test, if you put 4.179 as your value, or if you put 4.182 of your value, or if you put the average between those two, and you put a reasoning behind it, I would accept all three of those answers because I know you're thinking about what's going on there. If you put in 400 Kelvin, that's a problem. But if you said, hey, I think it's going to heat up, it might heat up to be 350 Kelvin, and so I'm going to use 325, I'd be okay with it, just as long as you understood why you're doing what you're doing. Okay? Not because Wanklin did it, because you understand. Okay, so I'm going to use 4.179 for my answer. 4.179 kilojoules per kilogram Kelvin. Okay, now I have everything I need. Let's go ahead and start plugging this in. Mass of the water is 15 kilograms, so 0.15 kilograms. 4.179 kilojoules per kilogram Kelvin. And then my temperature 2 minus my temperature 1, which is 30 degrees, and the temperature difference in Kelvin is the same as in Celsius, so I don't have to convert. Okay, I don't have to convert. I'm going to leave them as Celsius. But I do put a Kelvin here behind it because the difference between these two temperatures is Kelvin, and I want to make sure I can cross out my units. Make sure you understand what I just did there. Plus 0.25 kilograms times 0.385 kilojoules per kilogram Kelvin times T2 minus 30 is equal to 12 kilojoules. Okay, so here the only unknown is temperature 2. And when I solve for this temperature 2, I'm going to get a value in Celsius. Now, if you all are uncomfortable with this, convert all your temperatures to Kelvin, plug it in the equation, your answer is going to be in Kelvin, then you'd have to back it out and give it to me the answer in Celsius. So whatever you feel comfortable with. Okay, I'm not going to do the algebra here in front of you because it's going to take just some time, and I think you can all do the algebra. The temperature 2 here is going to show me it's 46.60 degrees Celsius, okay, and that's my answer. It would have been 319 Kelvin if I would have been doing it that way. So now that I get this answer, I have to think, does that make some sense? First of all, 46.6 degrees Celsius means it is still liquid. So my liquid approximation or my incompressible substance model is applicable, so that's good. I know I don't have to go back and recalculate. Secondly, 46.6 is about 319. So using the value for 300 Kelvin as my specific heat is reasonable. If I got this answer to be, again, 400, I would have had to then go and iterate and say, that solution is probably not good enough. I need to go back and pick a different value for my specific heat. Now, if I would go back now and say that 319, and I would go and come up with a different C sub P value, a more accurate C sub P value, my answer might be 46.58, and that's not worth the effort. Okay, that's not worth the effort. You probably can't even read the difference on that on a thermometer. Okay, you're going to say the temperature's 46 and a half. Okay, so only if it's a really big difference from what your assumption is, then you need to go back and work on it. So that's why we make those models and assumptions, but it's important that we have to verify that our models and assumptions are applicable at the very end of the problem. Elsewise, we have to go in and work on it. How are we feeling about this problem? Okay? All right. You would tell me if you had concerns, right? So here comes the exam problem that I gave. So here is the exam problem. You have a big tank and is full of 25 kilograms of water. And into that tank, you throw a very hot piece of iron. And it's I shouldn't say kilograms. It's actually, I'm put this one in English. It's in pounds, 25 pounds. Sorry about that. You put 1 pound of iron in it that's very hot. It's a quenching process. Maybe you're welding. Maybe you thought a fun activity this weekend would be to take a blowtorch and get a piece of iron really hot and throw it into water. Maybe. I don't know, whatever you do over the weekend, that's your own business. Okay. So I'm going to say here the water is initially at a temperature of 40 degrees Fahrenheit. Maybe it's a cool fall day. It's been sitting outside, 40 degrees Fahrenheit, and your iron temperature is going to be 1540 degrees Fahrenheit. Very, very, very hot. And we're going to throw that iron into that water, and we're going to quench it, which means that there's going to be a equilibrium temperature that's reached. And I want to find out, what is the temperature final? What is the final temperature of this water? Okay, so when I assigned this problem, students didn't know what to make their system. They didn't know what to do with their system. Even though, and then they had a homework problem very similar to this, but it caused a lot of problems. So I'm again going to make I can't look at just the iron, because the iron is losing heat to the water, and the water is gaining heat from the iron. And again, I can look at two first laws and put the Q out from one is equal to the Q in for the other, but I don't want to deal with all that. I'm going to make this whole thing my system. So it's going to be a closed system. Now, I assumed it's a closed system. Students asked me this morning, when we had a conversation, when I threw that hot metal into the water, wouldn't there be some initial, like some steam that would come off when that water hit when that iron hit the water? And the answer is yes. As it hit there, you would see this little bit of steam come up. And that, truthfully, would make that not a closed system anymore, because now water had left that system. But that's such a small amount that, again, we're modeling it for all intents and purposes, it's closed. There's not a massive amount of water leaving. So don't make things more complicated. We could make this problem very complicated, super complicated. But our job is to simplify it into a way that we can get a really good answer, and we have some really good models that we're following. Okay, so that's the first thing. It is a closed system. This tank's not moving anywhere, and it's not changing its height, so its kinetic energy and its potential energy effects are negligible. In this system, there's no electrical work, there's no mechanical work. Again, you can make the argument that boundary is going to change a little bit when that 1 pound of iron goes in, but it's going to be so small that, again, we don't have to worry about any boundary work. So let's not worry about that. Let's not worry about that small value, and let's take care of this work and get rid of it. Now let's talk about the heat transfer. If we put this tank out there, and it's a bigger tank, and we threw this small piece of metal into it, and we put our hands on the outside of the tank, we probably would not feel heat leaving the tank. Okay? The problem statement says here it's a well-insulated tank. So that takes out, I should probably say that it's a well-insulated tank. But we could probably make the assumption anyway that, you know what, this is not going to heat the tank up so much that we're going to feel a lot of heat coming out. Okay, so that's what this goes away. And so now we just have delta U is equal to 0. Okay, so what do we have? Inside our system we have two things. We're going to have the delta U of our water plus the delta U of our iron is equal to 0. We're going to expand these. This is going to be the mass times the internal energy 2 minus internal energy 1 of my water plus the mass of my iron times the internal energy 2 minus internal energy 1 of my iron, and that's going to equal 0. And I know, I'm sorry, people at home, you've been yelling at me because I haven't changed over my laptop. If you catch me here, people in class, that I haven't changed that screen over, let me know, because the people at home can only see what's on that screen. So again, I'm sorry, people. I think there's a total of like 7 people that watch these things at home, but I do apologize to you 7. Okay, just so take a screen cap of this, go back and listen to what I said. I'm sorry. I'm used to the old system. Okay, so here's our situation here. Now we know we don't have the properties for iron So I know I have to use incompressible substance. Water isn't, I'm assuming that the temperature is not going to get above 212 and boil, so I'm going to assume that we can still use incompressible substance for that. So this is going to be equal to the mass of the water times the specific heat of the water times T2 minus T1 of my water, plus the mass of my iron times the specific heat of my iron times the T2 minus the T1 of my iron. Okay. This equals 0. Now, what do we know in the problem statement? We know the mass of the water, and we know the mass of the iron. And we know the T1 and the T2, T1 of both the iron and the water, and they're different temperatures in this case. And we know they're going to come to a common equilibrium temperature that this T2, I could just rewrite it as T final. That's the temperature, it's the same temperature. Now we have to find out what our specific heats are. And so, I'm going to go to my document camera just for a moment, and then I'm going to come out of it so I don't leave you at home worried or just watching this thing and hearing my voice. We're going to go into our English tables, table A19E. Okay, now iron. They give me a value for the specific heat of 0.107, but this is at 540 Rankine, and man, we're at 2,000 Rankine. Okay, because if I add 460 to 1540, I'm at 2,000 Rankine. That's way off. But that's the only entry value we have. So we are going to assume that the specific heat is pretty constant there, and we're going to use 1.107. For water, it's at 40 degrees Fahrenheit, which is 500 degrees Rankine. And you know what, we don't have a 500 degree Rankine, but we do have a 495, and we have a 540. And I might make the argument that the temperature is going to rise, so if I can use some place in between these, if I can use the average of these two numbers, that might be the best value that I would use for C sub P. So that's what I'm going to do. I'm going to average these two numbers to use for my C sub P there. So now I'm going to go back to my laptop so those people at home can see. And I'm going to put in for my iron, I'm going to put in that the specific heat is equal to 1.107 BTUs per pound per degree Rankine. And my specific heat of my water I'm going to use, it's going to be equal to 1.006 plus 0.998 divided by 2. And this will give me 1.002 BTUs per pound per degree Rankine. So that's what I'm going to use for those two values. Now, when you look at this, I want you to have some physical understanding with what these specific heats mean. Which object is going to change their temperature the fastest? The water or the iron? The iron, and why? It has a lower specific heat. It needs less energy to change the temperature 1 degree. Okay? The higher the number, the harder it is to change the temperature. You have to have some idea about that. Don't just look at it as a number. Look at it as, what does it mean? What does that number mean? It's more helpful. Okay, so if I type this in here, now I'm going to get that my mass of my water, 25 pounds times 1.002 BTUs per pound per degree Rankine times temperature final minus 40 degrees, and this temperature difference in Fahrenheit is going to be the same as Rankine, plus we're going to have 1 pound times 0.107 BTUs per pound per degree Rankine times the temperature final minus my initial temperature, which was 1540, and that's going to be difference of degree Rankine, and that equals 0. And now we're back down to algebra, where we're going to find our answer that our final temperature is equal to 46.39 degrees Fahrenheit. Now you may make the argument that Dr. Wanklin, if you did not say that tank was insulated, that's a change of 6 degrees. I probably would feel some heat coming out of that tank. Okay, that's a fair thing that you could say. But it would be a small amount. It's not like it's changing the temperature hundreds of degrees. It's changing it 6 degrees. This problem, like I said, was on a test, and it's not very hard algebraically, but those decisions we had to make along the way about what to assume to go to 0. Hey, Mitzi, we had to think about those things, and those decisions cause problems. So make sure you're comfortable with those decisions. Now, what I said this morning is, how could I change this problem for a test? Give you the same ideas, but maybe now I would say, now you have 1 pound of iron that's at 1540 degrees Fahrenheit, and I want to dump it in to enough water that the water will only change by 2 degrees. The water's initial temperature is 40 degrees, 2 degrees. I could now do this same problem, and now I lock in the final temperature and find out what the mass is. How much water would I need to only have a temperature change of 2 degrees? And I could do the same thing by saying, okay, because there's density on this table A19E, I could ask you, okay, how much water? What's the volume of the tank that I would need to change that temperature 2 degrees? So we have to think about these problems. Okay, I know I practiced this problem in my homework. What's a way that we could look at it from a different angle to make sure I understand it that Dr. Wanklin may ask? Sometimes when I ask you a question on the exam, I'm going to go lockstep right in. And sometimes I'm going to come to you from a little bit different. Like on the exam that you had, exam 1, you knew that I was going to give you a problem with the cycles. Okay, the area where most people messed up is at the work. They couldn't figure out the work. Work is the area under the curve. Some people noticed, hey, I can just look at it's a triangle and a square, and I found the area under the curve. And some people tried to make it polytropic and do some things. I understand why you did that. I do understand. But it's a simpler method that I was asking for. Some people got it, some people didn't. It didn't wreck your problem if you didn't. You missed a few points. No big deal. But you need to think about, okay, work is area under the curve. I can understand, hey, look, that's an easy area for me to calculate. And that is, quote unquote, tricky, okay? Some people say your exams are tricky. Okay, my philosophy is it's only a trick if you don't understand it. That's what I believe. But I understand where you are sitting out there. It does look tricky. Okay, but that's the level of understanding I want you to have in this class. What questions do you have for this material? Now, if you go into heat transfer, this problem gets another level, and it's going to ask you things about time. How much time does it take to quench this? If I ever teach heat transfer again, I'm going to have a whole exam that's about food. How long does it take to chill a can of pop? How long does it take to hard boil an egg? How long does it take to cook a steak or portobello mushroom, I guess, for our vegetarian friends, to a certain temperature? That's what my whole exam is going to be. So if I ever get to teach that class again. But I'm here in thermo, which is a wonderful, wonderful class. That's all I have for you today. Have a good weekend. Stay out of trouble. And we'll see you here on Monday where we'll talk about gases, ideal gases.